Hey everyone, so as you guys can see, we are in 3.2. Let me go ahead and zoom out. I don't have my number there for us, but we are in 3.2, and we are working with trigonometric integrals. So as you guys can see, the problem that we have here is exactly what our description is. It's a trigonometric integral. It looks kind of gross. Let's talk about what techniques we could use to tackle this. So the techniques that we have so far in regard to integration, we have the power rule of integration, which is like the basic way of finding antiderivatives. And we have U substitution, which is super powerful. And we also have integration by parts, which we just learned in 3.1. So, okay, we have three techniques we could use. Let's maybe try U substitution. So let's do that. Let's do U sub. So if we do U sub, what should we let U be? Cosine or sine? The way that I always pick U when I'm just doing a U sub is I generally pick U to be the more complicated piece. And what do I mean by that? Well, usually it looks gross, or it is the problem. It is the thing that makes the integral problematic, or in this case, it has the highest power. So I'm going to say that U is going to be equal to sine. All right, so U is equal to sine x. What's du then? Well, du would be the derivative of that. So the derivative of sine x is cosine x, right? So we have cosine x dx. That looks good. Now if we do a U sub, let's see if this helps us out here. So if we do a U sub, we would actually have u to the fifth. And if you notice, these parts right here in my original integral are both represented with du, and that is nice. That is perfect. So we're just going to go ahead and put a du there, and that takes care of every single part in our original integral. It translates every single part in our original integral in terms of u. So we're doing great here. Let's go ahead and find the antiderivative with our power rule of integration, right? That's just going to be 1/6 u to the sixth, right? Add 1 to your exponent, divide by that same math. I just brought my coefficient out front instead of writing it underneath u. Hopefully you guys are good with that. And then we just add our plus c. Now, are we done? No, we're not quite done. Remember, if you start in x, if that's your original variable, you want to end in your original variable. So in this case, let's go ahead and replace u. So we'll just rewrite what u is, which is sine of x raised to the sixth power, and then we have our plus c. So that looks good to go. We are done with that problem. Not too crazy, right? What if I asked you, however, to now jump into dun. Let's go ahead and scroll down. This problem. Okay, it doesn't look too terrible. Definitely doesn't have a lot of parts. It's just sine raised to the fifth power. So you would say, okay, well, how should I tackle this? Should I do a U sub? Okay, let's figure out if we could do a U sub. So let's say that u, what would we let u be? Let's let u be sine, right? Just like we did last time. Cool. What's du? Du is cosine dx. Do you guys see a cosine dx anywhere up there? I don't. I mean, I see a dx. These parts match. I have a dx and a dx. However, I have no cosine in my original integral. So that's a problem. How can we fix this? How could we figure out how to rewrite my original integral? You may ask, and I'm going to show you guys how to do that. So what we actually want to do here is, let's check this out. So what we want to do here, I have a lot kind of like typed up. I'm just going to kind of ignore what I have typed up. You guys are welcome to read it. Or you know what? I'll just read it to you guys, okay? So to use substitution, you need the derivative of u, right? Which I just showed you guys. When I do that, I end up getting a problem. What is my problem? My problem is that I have cosine x dx, and I don't have that represented anywhere in my original integral. Now what do? What we are going to do is we're going to rewrite sine raised to the fifth power somehow. Now, since we need to have a cosine of x to show up in our original integral somehow, so that we can actually do a U-sub, what we are going to use is a trig identity that allows us to convert the following. So I'm going to erase all this crap, and we are going to move to a different space so that I have more room to talk, or more room to write. I have all the room to talk. There's no one in the room with me. I can talk all I want. Can't write though. So I'm going to do this right here. Check this out. Sine squared x is equal to 1 minus cosine squared x. Why is this important? This is important because I need a cosine x. So let's check out how I can do this. All right. So remember, our original integral is the integral of sine x raised to the 5th power, right? And then we have our dx. What I'm going to do is strip off a sine x. I'm going to strip off a sine x. So what does that look like? Well, it looks like this. I'm just going to do sine to the 4th times a sine x. I'm just stripping it off and just writing it a little bit differently. Cool. So now that I've done that, I'm going to rewrite my sine to the 4th. Why am I doing that? Because if you notice, this identity up here is in terms of sine squared. I don't quite have a recognizable, clear sine squared right now. So let's rewrite sine to the 4th. Okay, let me erase my blue lines here, and let's do exactly that. So the next step here, I'm going to say that sine squared x is raised to the 2nd power, right? Just to make it look a little bit different, but it's the same thing. And then I still have my sine x dx over here, right? I still have that. Okay, now we're getting somewhere. If you notice, now I have a sine squared, and I can utilize my identity. So let's do that right below. Okay, so we'll have the integral, and then inside of my parenthesis here, right, I'm going to use this identity. So the identity, it's typed up in your notes. I just pointed to it a little bit ago. Sine squared x is equal to cosine minus, 1 minus cosine squared x. So I'm going to write that there. 1 minus cosine squared x. That is equal to that, right? All right, so now that I've done this, let's go ahead and rewrite the rest of our crap. Sine x dx. And while this may look a little bit more complicated, I'm actually sitting in a much better position for U-sub. I promise you. You probably have looked at the notes before this lecture, and if you have, then you know where I'm going, and if you haven't, then this makes this more exciting. So now let's do U-sub. Okay, I'm going to say that U is the more complicated part. What's the more complicated part? In this case, the one that's raised to a higher power. This is just sine by itself. It's just the 1st power. However, this crap is definitely raised to a larger power, which means that I'm going to go ahead and say that that crap is going to be equal to U. And I'm not going to say 1 minus cosine squared is equal to U. I'm going to just say cosine. Just cosine x. Okay, what's du? Du is negative sine x. Okay, having that said, now let's see what happens when we do a U-sub. All right, so before I do the U-sub, however, I do need to write that I have a dx here. I can't forget that. And this negative, I'm just going to bring it to the front, so that's minus du is equal to sine x dx. Hopefully you guys are okay with that. Now let's do the U-sub. Let's do it in pink. Cool. Now let's do the U-sub. So we will have the integral of 1 minus u squared. Hopefully you guys can see that. Remember, this is u, and it's supposed to be squared. So there we are. And then the rest of this, sine x dx. Well, I have that represented right above me, or right above this line, in terms of minus du. Beautiful. Let's bring that negative, the negative that's in front of du, let's bring that to the front. So we have negative integral, and then we have 1 minus u squared du. All right. So now we're going to go ahead and I'm going to write sideways here instead of writing down. Let's go ahead and square this out, right? Or multiply it out. If we multiply it out, I'm just going to go ahead and expand it. So 1 minus u squared, just so I don't make a mistake here, 1 minus u squared du. All right, so if we FOIL this out, what did I do? I dropped the negative. Where did I drop the negative? It was supposed to be in the beginning of this integral. Let me go ahead and write it. Copy it down here. Now we're okay. If I FOIL this out, we're going to get the following. So we're going to get 1 minus 2u squared plus u to the 4th du. Okay, now this has become a very simple integral that you guys can just evaluate, find the antiderivative of, and you're good to go. So let's do that, exactly. So we have the minus u out front. Okay, so, or the minus out front, minus u, Jesus. Minus out front, I'm just going to make it really bold there. And then antiderivative of 1 is going to be u. Remember, this is all in terms of u, right? So antiderivative of 1 is u. And then we're going to have, I'll just write this all out. So 2u to the 3rd divided by 3, there's that, plus u to the 4th divided by 5. And we're going to close this, we're going to add a plus c. So there's that. We are not quite done, however. So remember what I told you guys, if you start with x, you have to end with the variable x. We're not quite there yet. We have everything in terms of u. So let's go ahead and do that right now. Do you remember what u was? Let's just go back and make sure we remember what u was. What did we say u was? All the way back here to our purple ink, u was equal to cosine x. So we need to zoom back in here and replace all the u's with cosine x. So we have negative on the outside, cosine x. Then we have minus 2/3 cosine x cubed plus, I'm going to rewrite this as 1/5 times cosine x to the 4th, close my bracket, add a plus c, and I'm done. Now, if you want to distribute the negative, you can. I think in the notes I do, so let's just go ahead and do that so that it's consistent with the notes. The final answer here is cosine x plus 2/3 cosine x cubed minus 1/5, and then we have cosine x to the 4th plus c. Now you guys can write this like this. So I'm specifically talking about this. You can write these like that, or instead of having them with like big old parentheses, you can just write these in red so you guys can see the difference. You can rewrite the 3's here and the 4 there, and just erase your pesky parentheses just to clean it up and make it look a little bit nicer. But that's our answer. So it's not too bad. I think this is, I don't know, trigonometric integrals sometimes can be pretty fun, especially once you get it down. I think they're fun. They're kind of like little puzzles. I don't know if you guys have realized this, but everything that you're doing is like a big old puzzle. So let's focus on this one here. So we have the integral of sine to the 6th times cosine to the 3rd x dx. What can we do? Well, we could probably do Usub. We could try it. We could figure out, see how it goes. What I'm probably going to do in this case, though, before I do a Usub, is just take a look at what I have. So if I do a Usub right now, if you guys notice, both of my sine and my cosine are both raised to powers. So the reason why this makes this difficult is because if I do a Usub, let's say, for instance, let's just say I do it, right? Let's say I say, let's let u be equal to sine. Okay, what's the derivative of sine? Okay, the derivative of sine is cosine. Cool. If I do my Usub, I'm just going to write on top of this. I would have u right here, u to the 6th, but my du is not in terms of cosine cubed. Like, what do I do with this, right? So I'm running into a problem here. I'm going to have to do something similar to what I did in the last problem in the sense that I play around with my powers here. So I'm either going to strip off a cosine or I'm going to strip off a sine. Now you guys can honestly do either, and you guys can practice doing either. But what I'm gonna do is strip off a cosine. All right, so check this out. So I'm gonna have sine to the sixth, and then I'm gonna have cosine squared. And then I'm gonna have my lingering cosine x that I stripped off. So there he is. Okay, so now that I've done that, you can either rewrite sine or rewrite cosine. And what do I mean by rewrite? What I'm speaking of is that identity that I had previously used. So in the last problem, I used the identity sine squared is equal to 1 minus cosine squared. So I'm going to use that again. I can use that in terms of cosine squared, right? Cosine squared is going to be equal to 1 minus sine squared. So I'm going to use that for this one here. Why that one? Well, because it's already in terms of cosine squared. So let's do that. Okay. So having that said, let's go ahead and rewrite it. All right. So I'm going to do this. So we're going to have the integral sine 6x. I'm going to write this so you guys can see, and this is in black. This is what we're rewriting. Rewriting this guy. This is going to be 1 minus sine squared x. And then we still have cosine x dx. Cool. All right, so now that we've done that, let's go ahead and declare what u is. Sorry, I don't know why I said that weird. Let's declare what u is. Okay, so what is u going to be? U is always going to be the more complicated thing that you have. I don't know why I talk like this when I'm making these videos, but the more complicated thing is sine, right? Sine is raised to 6 there, sine is like squared there, cosine is over here by himself, and you know, he's just the first power, so he's a nice guy. Let's go ahead and let's make u equal to the problem child, which is sine in this case. So u is going to be equal to sine x. Now what's du? Du is just the derivative of that, which comes out to be cosine x dx. Awesome. Now let's go ahead and do our u sub. Okay, so having that said, if we do our u sub, we're going to have the integral of u to the sixth times 1 minus u squared. And then what is this? Oh, isn't that nice? That's just du. Right? Cosine x dx, that's just du. So boom, there's du. Awesome. Way easier. Now let's go ahead and simplify as much as we can and then find the antiderivative. So if I distribute u to the 6th into my parentheses there, I'm going to have u to the 6th minus u to the 8th du. Now let's find the antiderivative. Okay, so that's going to be 1/7 u to the 7th minus 1/9 u to the 9th. Oh man, it's like a knife going through hot butter, right? Okay, I apologize. Okay, let's continue. So should we leave it like this? Is this good? No, it's not. Unfortunately, we do have to return to the variable that we started in. We did not start off in terms of u. We started in terms of x. What was u? U was sine x. Let's go back and replace. So our final answer here is going to be 1/7 sine to the 7th x minus 1/9 sine to the 9th x, and then our plus c, and we are done. Beautiful. Okay, let's keep working on here. Before we do that though, I have a strategy for you guys to take a look at every single time that you have a problem very similar to what we've been talking about. So the strategy for evaluating stuff, it looks like this, where you have cosine raised to some power and sine raised to some power, or in the exact order that we have here, sine raised to m, right, some power, cosine raised to n, some power. What's the strategy here? The strategy is the following. Number 1, if n is odd, so if the power of cosine is odd, save one cosine factor, right, and use this identity here. We did it before. We just did it. Okay, so what you'll do is you'll use that identity to change all the even powers of cosine. So once again, if cosine is odd, strip off a cosine, rewrite your even powers of cosine that you have remaining left, and use this identity. Then do a u sub, and you're going to let u be equal to sine x. Du is going to be, of course, cosine x. All right, so that is when the power of cosine is odd. Let's talk about if m is odd. So basically, if the power on sine is odd, what you're going to do in that case is strip off a power of sine, right? And this right here, typo. This right here, typo. It's supposed to be a 2. Okay, so again, if your power of sine is odd, strip off a power of sine, put it to the side. What's going to be left with sine? It's going to be now raised to an even power, right? So what I'm talking about is if you have sine raised to the 5th power, rewrite this. Strip off a power of, or strip off a sine, so you'll have sine to the 4x, and then you'll have sine x right beside it, right? So strip one off. That's what I'm talking about. Then what you'll do, you'll rewrite this remaining even power so that you can rewrite it and use the identity that I have right here. Once you do that, do a u sub, let u be equal to cosine, du is going to be negative sine. Bada bing, bada boom, you can figure it out. Now, if both are odd, if both your powers of sine and cosine are odd, like let's say you have this, sine to the 3x, I don't know, and then cosine to the 5x. You can do either one or two. You just pick which one. Doesn't matter which one you do. You can pick it either, and it will work out. I promise you. It sounds crazy, but it's true. 4. If both are even, and we haven't quite done this yet, but if both are even, you can use these identities here. Okay. All right, let's move on. What do we got left? We got a lot left. Example 2. Both are even. Okay, so I just circled those identities. We're going to go ahead and use those. Which ones am I talking about? These guys. We're going to use them. Probably. Right? Okay, so we're here at example 2. We want to go ahead and find the answer here. We have to integrate from 0 to pi of sine squared x, cosine squared x, and I'm going to drop the bounds for right now. I'm not going to work with the bounds until the very end. So let's just pretend we don't have them, and then at the very end we'll be like, oh yeah, we have bounds, let's plug them in. Okay, so in order to do this, I did circle those identities. We're going to use them. So let's go ahead and start off with just, I'm going to just pretend they're not there, pretend the bounds aren't there. So we have sine squared x times cosine squared x. We need to evaluate this. We're going to use both of those identities. So let's do that. All right, so for sine squared x, we're going to replace that with 1/2 1 minus cosine 2x. All right, and then cosine squared x, we're going to replace that with 1/2 1 plus cosine of 2x dx. Beautiful. I mean, it might not look beautiful, but it's actually pretty helpful. What can we do to clean this up and make this look less intimidating? The first thing that I can think of is bring these constants to the front. Let's get rid of them. Let's bring them out front. So instead of them having them there, let's write them out front. It's 1/2 times 1/2. That's going to be 1/4. Okay. So it's going to be 1/4. And let's see, what else? What else could we potentially do? So I don't know if you guys realize this, but you can rewrite this right here as 1 minus cosine squared of 2x. And of course we have our dx. The reason why we can do that, if you guys FOIL it out, it is going to simplify to be that, I promise. Why is that so? Because 1 times 1 is 1, and then if you guys notice, these middle terms that you would eventually multiply together are going to cancel out, and you have a negative cosine 2x times a positive cosine 2x, which leaves you with a negative cosine squared 2x. So I didn't do anything too crazy. I just multiplied them out, and it actually condensed to be exactly what you guys see there. Cool. Okay, so now that we have that, we are actually going to rewrite this again. So we're going to rewrite this part right here. The cosine squared 2x. We're actually going to use another identity to go ahead and rewrite this. So I'm going to go ahead and scroll down, give myself a little bit more room. So we're going to have 1/4 still out front, and we have 1. And then we need to go ahead and rewrite cosine squared 2x, and we're going to use an identity to do that. So we're going to have 1/2, and then we will have 1 plus cosine 4x dx. Okay, so now that we've done this, let's go ahead and distribute this 1/2 in here. So we'll distribute it to both of these terms. And so we'll end up with 1/4 out front times the integral of 1 minus 1/2 plus 1/2 cosine to the 4x, or cosine of 4x, sorry, and then dx. Awesome. Okay, so now that we're at this juncture, what we can do is just go ahead and combine like terms. So, oh, I'm running out of space already. Okay, so combine these two right here. What we're going to end up with is just 1/2. So we have 1/4 and 1/2 plus 1/2 cosine of 4x dx. So at this point in time, this is a pretty doable integral, I think. So you guys could factor out a 1/2 if you would like. And if you factor out a 1/2, what you're going to end up with is 1/8. And you'll end up with just 1 minus cosine. I guess you guys could have done this step earlier, but whatever. We're doing it now. So you have 1/8 times the integral of 1 minus cosine 4x dx. Let's go ahead and find the antiderivative of this. I'm just going to work sideways because I clearly have run out of space. If you guys see, I have the next box there. So we're going to end up with 1/8. Now, the antiderivative of 1 is just going to be x, and then we are going to end up probably having to do a u sub to take care of the 4x that's inside the argument there of cosine. And when you guys do that, you'll end up with basically just, I'm going to skip that step and hold you guys to it. U there is going to be equal to 4x. You guys can finish that off. But what you will end up with is 1/4 sine of 4x. You guys could probably see that coming. And then we'll just have a plus c on the end. So you guys could finish that if you'd like in terms of distributing the 1/8. Now, I do recall that we had bounds, right? So we're not going to have a plus c because we actually do have to plug in boundaries that I told you that we were specifically going to ignore until the end. So now that we are at the end, we do need to evaluate this thing specifically from 0 to pi. So let me go ahead and scoot on over, and we will do this over here. Okay, so if you evaluate these, you guys are welcome to actually like plug and chug and put it in your calculators. What you will end up with is probably a decimal answer if you do put it in your calculator, but it will be equivalent to 1/8 pi. And there you guys go. So if any of this scared you, just brush up on your trig identities. The ones that I give you in this lecture video are pretty much the ones that you're going to be utilizing for the majority of 3.2. So it's just helpful to just go over them and then just be aware that you have those inside of your toolbox that you can draw from. So pretty much stick to, you know, what I give you up here. I give you this identity, right? This one here, there's a typo, that's supposed to be a 2, and then these two down here, which is what I've been using. So, all right, keep moving on. So that was example 2. Now we're going to talk about strategies of, wow, I didn't say that right. Strategies of tangent and secant. So far we've only been working with powers of sine and cosine, rewriting them in such a way that we can use our trig identity. Once we have our trig identity plugged in there, then we can do u substitution and everything works out nice. Okay, so we haven't done it for tangent and secant. The same goes for tangent and secant. You just work with the identity for secant squared and for tangent squared. That's it. That's the only big difference. The same method is going to be used. So let's just break this down for a second. All right, so let's say we have tangent raised to some power of m. Let's say we have secant raised to some power of n. Now, if n, so we're talking about the power of secant, if the power of secant is even, what you're going to do is you're going to write all the other secant squares as secant squared is equal to 1 plus tangent squared x. Then what you want to do is a u sub. You'll say u is equal to tan x, du is equal to secant squared x, and it's going to fall apart like butter. Or butter doesn't fall apart. I mean, whatever, you get it. Okay, the step 2. So if m is odd, what is m? What is m referring to? M is referring to the power of tangent. So if the power of tangent is odd, save one factor, so strip off or siphon off, whatever you want to call it, strip off a power of secant x and 1 tangent x. So save one factor of secant x and 1 factor of tangent x. Rewrite all the other tangent squares as secant squared x minus 1. Then use u sub. What you're going to do is you're going to let u be equal to secant x. And then you're going to go ahead and see that tu is equal to secant tangent. So it will make sense when you're doing it. Following this strategy is helpful. However, if you just want to like bulldoze through problems and discover it on your own, you can do that as well. Let's go ahead and take a look at a problem. So right here, tangent is raised to the 6th power. Secant is raised to the 4th power. Now there's several ways that you can do these types of problems. Well, there's probably only 2 really. So what I'm going to do, however, is I'm going to rewrite, or I'm rather going to strip off or pull off 1 factor of secant squared. So check this out. Let's do it. Let's do it in a different color. Let's do a color that we haven't done. I don't know. Well, let's see. Let's do a green. Okay, let's do that. Okay, so let's do exactly what I said. And we're gonna break up the secant to the 4th power. So I'm gonna keep tangent to the 6th. I'm gonna break up secant to the 4th so that I rewrite it as 2 secant squares. There they are. I broke them up. Cool. Now what? Well, now what I'm going to do is I'm purposely going to target one of the secant squares. Let's say I target this one. I'm going to use my identity and rewrite. So I'm going to do this over to the side. I'm going to say that secant squared x is equal to 1 plus tangent squared x. I'm going to use that to my advantage. We're going to replace what I've just underlined here, this part, secant squared, with that. All right, so let's do it. So let me zoom in just a tad. I always write nicer when I zoom in. So we have tangent to the 6th x. Okay, we're going to rewrite this next part, right, with our identity. So this is going to be 1 plus tangent squared x. All right, and then we still have secant squared over here. And we still have our dx. Okay, might look like I'm not getting anywhere, but I promise I am. Now it's time for u sub. So we've broken apart our powers. We've targeted a specific, trig function to do, right? We targeted it. We broke up the powers. Now it's time for u sub. What are we going to let u be? We're going to let u be the thing that is raised to the biggest powers. What is that? That looks like this guy here, tangent. Tangent is raised to the 6th power, and then again in here we have another representation of tangent. So tangent's the more problematic thing here. So let's let u be tangent. Okay, so u is equal to tan x. Okay, what's du? Du is the derivative of tangent, which is just secant squared. So we have secant squared dx. Beautiful. Let's go in and do our u sub. Check this out. This is going to be u to the 6th. This is going to be u squared. This right here is represented with du. Sweet. Okay, let's go ahead and do our u sub. So, all right, let's write this out. So we have u to the 6th, 1 plus u squared, and then du. That's not too bad. Okay, looks super familiar. We actually had another integral that when we did u sub, it became like identical to what we currently have. So let's work sideways. All right, so if we multiply out, we're going to have u to the 6th plus u to the 8th du. Let's find the antiderivative. We're going to have 1/7 u to the 7th plus 1/9 u to the 9th plus c. Are we done yet? Can we leave it like this? No, we can't. So if we started with x, we have to end in x. We can't leave it in u. So therefore, let's finalize this. Let's go ahead and rewrite what u is. So we're going to have 1/7. What was u? U is tangent x, right? So we have 1/7 tangent to the 7, right? Or tangent x raised to the 7th, rather, plus 1/9 tangent to the 9th plus c. And that's our final answer, guys. So it's not too terrible. Like I said, these are kind of fun once you get the hang of it and realize you can use your identities to your advantage. It becomes kind of fun, I promise. Okay, the next one. Let's move on here. Let's see what else we got. So the next one we got is example 4, and we have secant to the 9th, and we have tangent to the 5th. So as you guys can see, the power of tangent is odd. So in this case, what I'm going to do is I'm going to pull out a factor of secant x and tangent x. So check this out. I feel so cool when I say like check this out, but I don't know if you guys actually think this is cool. I do, but who am I, right? Okay, so let's do exactly that. Let's pull out a factor of secant. Let's pull out a factor of tangent. Okay, so if we do that, it's going to leave us with the following. Okay, so I'm going to strip off a power of secant. That's going to leave me with secant to the 8th, right? And if I strip off a power of tangent, that's going to leave me with tangent to the 4th. And I'm going to write those parts that I stripped off at the end, right? So I'm going to have secant over here, and I'm going to have tangent over here. And I have my dx. Okay, it looks ugly. It looks like I'm making it worse, but I promise it's going to get better. Now what do we do? Okay, so now what I am going to do is I'm going to target tangent right here. I'm going to target this thing. So I know that my identity is always in terms of like secant squared, right? Or tangent squared. This is not quite tangent squared. It's tangent to the 4th. So what I need to do is rewrite this thing so that it does look like tangent squared. How can I do that? Super simple. Let's play around with the powers. So I'm going to do another line here. So once again, we have secant to the 8th. Let's rewrite this as tangent squared squared. And then I'll copy the rest of my stuff down over here. Okay, so now that I can visibly see that I have tangent squared, I can use my identity. And we're going to go ahead and do that right now. So we have secant to the 8th. Inside of here, let's use our identity. I'm just going to change colors so you guys can see exactly where I'm putting it in. We have secant squared x minus 1. There it is. And then the rest of the stuff, right? Secant x tangent x dx. Cool. Now what? Well, so we've kind of, first and foremost, did a little bit of an analysis, figured out what power was odd, what case did we have, decided to purposely strip off secant and tangent. Then we said, okay, tangent, I'm going to rewrite this so that I can see it as tangent squared and I can use my identity. Now I would say use u sub. What is u going to be? U is going to be the more complicated part. What is raised to the highest power? secant, right? I got secant to the 8th over here. Let's let u be equal to secant then. Okay, so let's do that down here. All right, so u is going to be equal to secant x. What is du? All right, du is going to be what? Secant x tangent x. Oh man, that's pretty sweet. Why is that sweet? Because that's right here in my original integral. That looks nice. Okay, let's do our Usub. So let's see, what do we got? We're going to have the integral of u to the 8th. Then we're going to have u squared minus 1 squared. And then we're going to have du. Du is representing all the rest of this, which is perfect. All right, so now that we have that going on, let's work with everything in terms of u. So we are going to have to FOIL this out, right? If we FOIL that out, and you guys, I know you guys can do that. I'm just going to skip the steps of literally FOILing it out, just writing what it is. So it's going to be u to the 4th minus 2u squared, and then plus 1. And we have our du. Now we have to go ahead and distribute u to the 8th. So we're going to have what? Remember, the base is the same, so you add the exponents. So we're going to have u to the 12th minus 2u to the 10th plus u to the 8th du. We are almost done, guys, with this problem anyway. Now antiderivatives, right? So we are going to have 1/13th u to the 13th minus, let's see, what are we going to have? 2 divided by 11, u to the 11th, plus 1 over 9, u to the 9th, and then our plus c. Can we leave it like this? No, we cannot. If you put this in WebWork, like if this was your problem in WebWork, it's not going to like it. You need to rewrite things in terms of the original variable. So in this case, what was u? Let's zoom back out. Let's just refresh our memories here. U was secant x. So let's go in here and replace everything with what it needs to be. So we have 1/13 secant to the 13th minus 2/11 secant to the 11th plus 1/9 secant to the 9th. And then we have plus c. So that's awesome. There we go. So not too bad, right? Hopefully not too bad. Hopefully maybe you guys like this better than integration by parts. To be honest, I liked this better than integration by parts when I first learned it. It just kind of like clicked a little bit more. It didn't seem as intimidating. I don't know about you. That's the way it worked for me. Let's go ahead and look at another problem though. So example 5 here. Example 5. Okay, so this is a little bit different of a problem. It says show. So it wants us to show something. It wants us to prove something. So we have the integral of secant x dx is equal to ln of the absolute value of secant x plus tangent x plus c. We want to prove this, or we just kind of want to show that it is valid. Okay, so unfortunately, this integral requires a little bit of a trick. And if you were in Calc 1 with me, you did learn about that little trick. And the little trick was multiplying your original integral by a special 1. What does a special 1 mean? Well, remember that the ratio of anything over itself, so like 2/2, that's 1, right? 3/3, that's 1. X over x, that's 1. So what I mean by a special 1 is a special fraction that's going to allow you to evaluate this original integral right here, the integral of secant x dx. Okay, what's the special 1? Well, the special 1, you got to know about it, right? Got to kind of have to be told about it before you will honestly think about it, because it's not super intuitive. Let me tell you, if I was faced with just solving this integral here by myself and I wasn't told about the special 1, I would probably end up crying after hours of not being able to do it because it's not intuitive. So let's remind those that may have forgotten, or for those that didn't take Calc 1 with me, what the special 1 is. Okay, so the special 1, now that I've chalked it up, it's just going to be secant x plus tangent x divided by itself. So secant x plus tangent x. That's the special 1. secant x plus tangent x divided by secant x plus tangent x is just 1. But this is the special one that you need to actually multiply your original integral by in order to be able to do a u sub. So what I'm going to do is solve the original integral to show you that it's equal to this right here. Okay, so the reason why this is important is because it's just going to refresh your memory on this technique so that if you do run into this, you will be able to utilize it. Okay, so let's do it. So our original integral is secant x dx, right? So I'm going to just multiply this by that special one. All right, and there she is. And then we'll just add our dx. Cool. So now that we have that, we can go ahead and actually do a u sub, whether you believe it or not. What are we going to let u be? You may ask. Well, let's let u, do this in green, let's let u be equal to secant x tangent x. So secant x plus tangent x. Sorry, secant x plus tangent x. There we go. What's the derivative of that? What is du, you may ask? Let's do that next. So the derivative of secant x is secant x tangent x. And the derivative of tangent x is, you guessed it, secant squared x. And of course we have a dx here. How does this help us? This looks so gross, you may say. It actually looks right on track with where it needs to be. So if we go in and do our u sub here, let's do this in red. So we have the integral, and if you guys notice, if we were to, before we do our u sub, if we were to multiply secant x in here, let's just do that first before we do our u sub. What I'm actually going to end up with is secant squared x plus secant x tangent x. And then on the bottom, I still have the remaining, or the original denominator, secant x plus tangent x, right? I still have my dx over here. Okay, where am I getting at? If you guys notice, this right here is exactly this top part. It's exactly this top part right here. That's u. I mean, that is du. Sorry. What is u, you may ask? It's this right here. That's u. Okay, so now let's do our u sub. Okay, let's do this over here. We're going to have basically du divided by u. Okay, so du divided by u. What's another way of looking at that? The way of looking at that is 1 over u times du, right? All right, what's the antiderivative of 1 over u? It's always ln of the absolute value of u plus c. All right, what is u? Because remember, we started with x, we have to end with x. So if we go in and replace what u is this right here. I just underlined it in blue. U is secant x plus tangent x. Close my absolute value, add my c. And if you guys notice, this answer is exactly, move my little tool here. It's exactly what we have there. Let me shrink this so it's on the same screen. You guys see that? So we've proved it. We've shown that if I take my original integral and actually integrate, I end up getting the same answer as what's in my box there. So cool. So there you guys have it. So just remember that technique. It works for a couple other integrals. I'll leave it up to you to discover which ones it is. But for now, what we're going to do is another example. So if we move on here to example 6. So example 6, we have to find the integral